Hi everyone, welcome to our physics class. In the previous class, we have studied about magnetic flux, meaning of electromagnetic induction, experimental demonstrations of electromagnetic induction, that is coil magnet experiment and coil experiment. So this is electromagnetic induction part 2. Okay, well, let's start today's class. So in this class, first let us discuss about the next very important concept, that is the Lenz's law. This is very interesting topic. So first here, let us consider a Bohr magnet. So what is the meaning of a Bohr magnet? Any rectangular or cylindrical object that has a magnetic field is called a Bohr magnet, right? So this is a coil that is connected to a sensitive galvanometer. So when the south pole of a Bohr magnet is moving towards the coil. So what happens? The number of magnetic field lines passing through the turns of the coil will change, right? When south pole of Bohr magnet is moving towards the coil, the number of magnetic field lines passing through the turns of the coil changes, so produces the EMF. So actually that is flowing in clockwise direction. So this EMF actually opposes the further change of the magnetic flux. So this point is very important. So when the EMF induced in the coil, so that EMF opposes the further change of the magnetic flux. Actually here the direction of induced EMF is clockwise. That means the face of the coil is just behaves like a south pole, right? So when the south pole of a Bohr magnet is taken away from the coil, again, the number of magnetic field lines passing through the turns of the coil will changes. EMF induces in the coil, produces the induced current. Okay, so actually that is flowing in anti-clockwise direction. Okay, so this one opposes the further change of the magnetic flux. So this clearly shows that the direction of induced EMF, the direction of induced EMF is such that it opposes the cause producing the change of magnetic flux. Actually, this is the statement of Lenz's law. The direction of induced EMF is such that it opposes the cause producing the change of magnetic flux. Okay. Suppose when the north pole of Bohr magnet that is moving towards the face of the loop. So what happens? The number of magnetic field lines passing through the loop will changes. EMF induces in the loop. EMF induces in the loop. So produces the induced current. So actually, that is flowing in which direction? That is actually flowing in anti-clockwise direction, because that opposes opposes the further change of the magnetic flux. Now actually the face of the loop is just behaves like a north pole, right? The face of the loop in which current flows anti-clockwise, that face is just behaves like north pole. Okay, so this one opposes. Now the loop opposes the further change. Okay, so now the direction of induced current that will oppose us, the further change of the magnetic flux. So when the north pole of Bohr magnet is moving towards the face of the loop, so what happens? The number of magnetic field lines passing through the loop will changes. EMF induced in the loop produces the induced current that is actually flowing in anti-clockwise direction. So now the face of the loop is just behaves like north pole, and the direction of induced current opposes the further change of the magnetic flux. Okay, suppose when the north pole of Bohr magnet is moving away from the face of the loop. North pole of Bohr magnet is moving away from the loop. So again, the magnetic field lines passing through the loop will changes. EMF induced in the loop produces the induced current, but that is flowing like this. It's flowing in clockwise direction. So the face of the loop in which current flows clockwise, that face is just behaves like a south pole, right? The face of the loop in which current flows clockwise, that face is just behaves like south pole. Now this south pole opposes the further change of the magnetic flux. Okay, so what is the statement of the Lenz's law? Now we can easily define the statement. According to Lenz's law, the direction of induced EMF, is such that it opposes the cause. It opposes the cause producing. It opposes the cause producing the change of magnetic flux. Change of magnetic flux. So what is the statement of Lenz's law? The direction of induced EMF is such that it opposes the cause producing the change of magnetic flux. So this is the statement of Lenz's law. The explanation is very, very simple. When south pole of Bohr magnet is moving towards the coil, south pole of Bohr magnet is moving towards the coil. So what is the direction of current in the coil? That is in clockwise. Now the face of the coil is just behaves like south pole, and this one opposes the further change of the magnetic flux. Is it not? Suppose when south pole of Bohr magnet is taken away from the coil, the number of magnetic field lines passing through the turns of the coil will change as EMF produces the induced current that is flowing in anti-clockwise direction. Now the face of the coil is just behaves like north pole, and this one opposes the further change of the magnetic flux. So the direction of induced EMF, the direction of induced current is such that it will always opposes the cause producing the change of the magnetic flux. Okay, So when north pole of Bohr magnet is moving towards the face of the loop, what happens? The number of magnetic field lines passing through the loop, it changes. So the EMF induced in the loop produces the induced current that is actually flowing in anti-clockwise direction. Is it not? So when north pole of Bohr magnet is moving towards the loop, what happens? The number of magnetic field lines passing through the loop will changes. EMF induces, produces the induced current that is flowing in anti-clockwise direction. That means the face of the loop is just behaves like north pole. That one opposes the further change of the magnetic flux. So when north pole of Bohr magnet is taken away from the loop, north pole of Bohr magnet is taken away from the loop. Again, the number of magnetic field lines passing through the loop will changes. EMF induces, produces the induced current. Okay, so that is actually flowing in clockwise direction. Now the face of the loop is just behaves like south pole. So this one opposes the further change of the magnetic flux. Okay, so when south pole of Bohr magnet is moving towards the coil, the direction of induced current in the coil is clockwise direction. When south pole of Bohr magnet is taken away from the coil, the direction of induced current in the coil that is in anti-clockwise direction. When north pole of Bohr magnet is moving towards the coil or loop, what is the direction of current in the loop? That is in anti-clockwise direction. When north pole of Bohr magnet is taken away from the coil, what is the direction of current in the coil? That is in clockwise direction. So what is the statement of Lenz's law? The direction of induced EMF. The direction of induced EMF is such that it opposes the cause producing the change of the magnetic flux. So actually Lenz is the scientist who gave the direction of the induced EMF. So what is the significance of Lenz's law? So this is very important. The significance of Lenz's law. Significance of Lenz's law. The first significance is Lenz's law is a consequence of law of conservation of energy. Okay, so Lenz's law is the consequence. Lenz's law is the consequence of a law of conservation of energy. The conservation of energy means energy can neither be created nor be destroyed, but it can be converted from one form to another form. Actually here the mechanical energy that is converted into electrical energy. Is it not? When south pole of Bohr magnet is moving towards the coil, okay, so actually the mechanical energy that is converted into electrical energy, right? So the second significance of the Lenz's law. So actually Lenz's law gives the polarity of induced EMF, gives the direction of induced EMF, right? So that is also the significance of Lenz's law. So what is the consequence of Lenz's law? That is law of conservation of energy. What is the consequence of Lenz's law? The consequence of Lenz's law, that is the law of conservation of energy. Lenz's law is based on law of conservation of energy. So in Lenz's law, actually the mechanical energy is converted into the electrical energy. So Lenz's law actually gives the polarity of induced EMF. Lenz's law gives the polarity, that means the polarity or direction of induced EMF. So name the law which gives the direction of induced EMF. Is that Lenz's law? Lenz's law gives the direction of induced EMF. Name the scientist who gave the direction of induced EMF. Lenz. So what is the consequence of Lenz's law? Law of conservation of energy. Okay, so these are the two significance of Lenz's law. Number one, the consequence of law of conservation of energy, and Lenz's law gives the polarity of induced EMF. Lenz's law gives the direction of induced EMF. What is the statement of Lenz's law? The direction of induced EMF, is such that it opposes the cause producing the change of the magnetic flux. Okay, the next topic, that is derivation of the expression for the motional EMF and force required to pull a rod in the presence of perpendicular uniform magnetic field. Okay. So first here, let us consider a closed conducting path. First here, let us consider a closed conducting path, that is P, Q, or S. So here P, Q, or S is a closed conducting path. P, Q, or S is a closed conducting path. So with the arm PQ, that is sliding. So this is a sliding rod. PQ is a sliding rod. PQ or S is a closed conducting path. Actually, the plane of the loop that is placed in the presence of a perpendicular uniform magnetic field. Okay, the plane of the loop that is perpendicular to uniform magnetic field. Actually here cross mark indicates the direction of magnetic field lines that is directed normally inwards, directed into the plane of the diagram, plane of the screen. Is it not? The cross mark crosses shows the perpendicular uniform magnetic field. So direction is normally inwards, directed into the plane of the diagram. So PQ or S is a closed conducting path with on PQ. So this is sliding. This is a sliding rod. Okay. The plane of the loop is placed in the presence of the perpendicular uniform magnetic field. So actually here the arm PQ is sliding towards left with some velocity v. Okay. So now we can choose the distance from PQ to RS. The distance from PQ to RS, let us consider this distance as X. Okay, so when the arm PQ is moving towards left, actually the magnetic field remains constant. So L is the length of the rod, so that is also remains constant. But X is variable. When PQ is moving towards left, X will changes. Is it not? So what is the total magnetic flux linked with this loop? So here, first we have to calculate the total magnetic flux, total magnetic flux linked with the loop is P, Q, or S. So the magnetic flux means the product of magnetic field vector and the area vector. So dot product of two vectors, that is given by the product of magnitude of two vectors. That means the magnitude of B vector, magnitude of A vector, magnitude of B vector is B, magnitude of A vector is A, and cosine of the angle in between B vector and A vector. So here B vector is normally inverse, A vector is also normally inverse. Is it not? B vector is normally inverse, A vector is also normally inverse. Okay, so B vector is parallel to A vector. So what is the angle in between them? Angle in between them, that is equal to 0 degree. Okay, so B into A means the area of the loop. Area is length into breadth. That means RS into SP. RS is L, SP is X. So area is length into breadth. L into X. L into X. So cos 0 is 1. So what is this? This is the magnetic flux linked with the loop. But we have to calculate the EMF induced in a conductor, that is due to the motion of the conductor. So that is placed in the presence of perpendicular uniform magnetic field. So what is the meaning of motional EMF? EMF induced in a conductor due to its motion. Okay, EMF induced in a conductor due to its motion and the presence of a perpendicular uniform magnetic field. EMF induced due to motion of the conductor. EMF induced due to motion of the conductor in a perpendicular uniform magnetic field. Okay, so that can be calculated by using Faraday's second law of electromagnetic induction. According to Faraday's second law of electromagnetic induction, Faraday's second law of electromagnetic induction, that is E is equal to minus d phi divided by dt. But here let us take the magnitude. So R is equal to minus d phi by dt. So negative sign indicates actually the direction of induced EMF opposes the change of magnetic flux. So what is the significance of negative sign? Negative sign indicates the direction of induced EMF, opposes the change of magnetic flux. So according to Lenz's law, the mathematical expression for EMF induced in a coil or loop is E is equal to minus d phi by dt. So this is actually called Faraday's law of induction. Okay. Actually, this mathematical expression is called Faraday's law of induction. What is this? This is Faraday's law of induction. So this is also called the Newman's law. Newman's law. So we have just studied this one. What is this? Lenz's law. So according to Lenz's law, the direction of induced EMF is such that it opposes the cause producing the change of magnetic flux. Okay, so this is also called the Faraday's law of induction. That is also called the Newman's law. So actually here negative sign indicates the direction of induced EMF is such that it opposes negative sign indicates the direction of induced EMF is such that it opposes the cause producing the change of the magnetic flux. Okay, so when the rod is moving towards left, when the rod is moving towards left, then V is equal to minus dx by dt. So this is the rate of change of displacement. V is the velocity of the rod. The negative sign indicates the motion of rod decreases the value of x. That is the significance of negative sign here. Negative sign indicates the motion of the rod decreases the value of displacement. Okay. So call this as equation number 1. Call this as equation number 2. Call this as equation number 3. Okay. So now equation 1 in equation 2, that is gives rise to E is equal to minus d by dt of what is the value of phi? Phi is BLX. So while differentiating the constant terms, that should be taken as outside. So here the magnetic field is constant, length of the rod is constant, B is constant, L is constant, but X is variable. Is it not? X is variable. So while differentiating the constant terms, that should be taken as outside. So BL is taken as outside minus BL into dx by dt. So E is equal to BL, the minus dx by dt. What is that? That is the velocity. So this is the mathematical expression for motional EMF. E is equal to BLV. So motional EMF is directly proportional to the strength of the magnetic field. Motional EMF is directly proportional to strength of the magnetic field. Motional EMF is directly proportional to length of the conductor, and the motional EMF is directly proportional to the speed of the conductor. That means the velocity of the rod. Okay. Okay, next we have to calculate what amount of force that is required to pull a rod in the presence of perpendicular uniform magnetic field. Actually, here the mechanical power is converted into electric power, but at equilibrium, at equilibrium, the mechanical power is equal to the electric power. Mechanical power, that is equal to mechanical power, that is equal to electric. Mechanical power is equal to electric power. Okay. So mechanical power, what is the meaning of power? Power is the rate of doing work, W by T. So this is a mathematical expression. Work done is force into displacement. Is it not? So displacement divided by time, the rate of change of displacement, what is that? Velocity. So P is equal to F into V. So this is a mathematical expression for mechanical power. So mechanical power is FV. Electric power, power is again the rate of doing work, but here work done when a charged particle is moving in under the potential difference V volt, the work done is VQ, is it not? The charged particle Q is moving under the potential difference V volt, and the work done is VQ divided by T. So Q by T, the rate of flow of charge, that is electric current. So P is equal to VI. So here V is E, that is the motional EMF, right? So this is the electric power, E into I. So according to Ohm's law, V is equal to IR, but here E is equal to I into R. So I is equal to E by R. So I is the induced current. What is the meaning of I? I is the induced current in the rod. So the direction of induced current in the rod, so that can be calculated by using Fleming's right hand rule. Fleming is the scientist who gave the direction of induced current. Lenz is the scientist who gave the direction of induced EMF. Fleming is the scientist who gave the direction of induced current. So, what is the statement of Fleming's right hand rule? Stretch out the first three fingers. Okay, look at this diagram. Stretch out the first three fingers of right hand in three mutually perpendicular directions. Four finger points in the direction of magnetic field. So middle finger points in the direction of induced current. Thumb points in the direction of motion of the conductor. So here the direction of induced current in the rod, so that can be calculated, that can be determined by applying the Fleming's right hand rule, right? Stretch out the first three fingers of right hand in three mutually perpendicular directions. Four finger points in the direction of magnetic field, the middle finger points in the direction of current, thumb points in the direction of motion of the conductor. So here direction of magnetic field, that is normally inwards, right? So the motion of the conductor, that is towards left. So what is the direction of current flowing in the rod? That is vertically downwards. The direction of current in the rod, so that is vertically downwards, right? Okay. So E is motional EMF, that is BLV divided by R. So now the above equation becomes FV, that is equal to E. What is the value of I? I is E divided by R. So it can also be written in the form of E square divided by R. So FV, that is equal to E square means BLV whole square, that is B square L square V square divided by R. 1 V get cancelled. So finally we will get F is equal to B square L square V divided by R. So this is the mathematical expression for the force required to pull a rod. Mathematical expression for force required to pull a rod in the presence of uniform perpendicular magnetic field. So this is the mathematical expression for motional EMF E is equal to BLV, and this is the mathematical expression for force required to pull a rod in the presence of perpendicular uniform magnetic field. So what is the meaning of motional EMF? The EMF induced due to the motion of the conductor in a perpendicular uniform magnetic field. EMF induced due to the motion of the conductor. EMF induced due to motion of the conductor where in a perpendicular uniform magnetic field. Okay, the next topic is self-induction. Self-induction. First here, let us consider a coil of wire. Actually, this is called an inductor that is connected to a battery through a plug key. When the key is opened, there is no current in the coil. But when the key is closed, so what happens when the key is closed? Current flowing through the key is closed. Current flowing through the coil, that is, gradually increases. Current flowing through the coil gradually increases from 0 to maximum. Im is the maximum current in the coil. Okay. So when current flowing through the coil is gradually increases, so then the magnetic flux linked with the coil, that is also gradually increases from 0 to maximum. So this is the maximum magnetic flux linked with the coil. So magnetic flux increases means the magnetic flux linked with the coil will changes. Whenever the magnetic flux linked with the coil changes, what happens? EMF induced in the coil, according to Lenz's law, that EMF opposes the further change of the magnetic flux. So that EMF is called the back EMF. Okay, so the EMF which opposes the direction of current. This is called the back EMF. Back EMF means the EMF which opposes the direction of current. So when current in the coil reaches a steady value, there is no change in magnetic flux. So in that case, there is no EMF in the coil. Okay. So when current in the coil reaches a steady value, there is no change in magnetic flux. There is no EMF in the coil. So when the key is opened, what happens when the key is opened? When the key is opened, so the current in the coil, that is, gradually decreases in the reverse direction. So this is decreasing current. This one is What is this? Decreasing current. So this is increasing current. Okay. So when current is gradually decreases in the coil, the magnetic flux linked with the coil, current gradually decreases. The magnetic flux linked with the coil is also gradually decreases. That means the magnetic flux linked with the coil changes. Whenever the magnetic flux linked with the coil changes, EMF induces. That EMF opposes the further change of magnetic flux. So that EMF is called the forward EMF. Forward EMF. Okay. So the EMF which opposes the decay current. EMF which opposes the decreasing current, that is called the forward EMF. The EMF which opposes the increasing current, that is growth current. The EMF which opposes the growth current, EMF which opposes the increasing current, that is called back EMF. The EMF which opposes the decreasing current, decay current, that is called the forward EMF. So which one is greater here? Let us consider a graph of current versus time in inductor. Actually, this is called inductor. What is the meaning of inductor? That is a circuit element which offers a certain opposition to any change in current. Inductor does not oppose the constant current, steady current. So it is having maximum infinite inductance but zero resistance. Inductor will opposes only the change in current. You know, resistor is a circuit element which offers certain opposition to the flow of current. Capacitor is a circuit element which stores the charge. Capacitor is a device used to store the electric charge. But inductor, so this is also a circuit element which offers certain opposition to change in current. It opposes the variable current, increasing current, decreasing current, growth current, or decay current. It does not oppose the constant current. Okay, so when switch on the circuit, so what happens? The current flowing through the coil is gradually increases. Let us consider T1 is time taken by the current to rise in the coil. So when current in the coil reaches a constant value, further increases the value of time, the current will remain constant. So when the switches off the circuit, so what happens? The current in the coil decreases. So this is, let us consider T2 is time taken by the current to fall. Time taken by the current to fall in the coil. So actually the time taken by current to rise is more than the time taken by current to fall in the coil. Is it not? Look at this graph. Time taken by current to rise in the coil, that is more than the time taken by current to fall in the coil. Okay, so based on this, we can easily conclude that which EMF is greater. So according to Faraday's second law of electromagnetic induction, E is equal to d phi by dt. So EMF is inversely proportional to time. As the time decreases, EMF induced in the coil will increase. Suppose if the time t is equal to 0, what is the value of EMF? EMF goes to infinity. Okay, actually here time taken by current to fall is less. So that means the forward EMF that is more than the back EMF. So T1 here more than T2. So that is why the forward EMF. Forward EMF. So this is more than the back EMF. What is the meaning of back EMF? The EMF which opposes the increasing current, growth current. What is the meaning of forward EMF? The EMF which opposes decreasing current, decay current. So now we can easily define what is the meaning of self-induction. Self-induction means whenever the magnetic flux linked with a coil changes. Whenever the magnetic flux linked with a coil changes, an EMF induced in the same coil. That is called self-induction. What is the meaning of self-induction? Whenever the magnetic flux linked with a coil changes, an EMF induced in the same coil, that is self-induction. Or the property of a coil by virtue of which it opposes growth or decay of current flowing through it. The property of a coil by virtue of which increasing current flowing through it, decreasing current flowing through it, is it not the property of a coil by virtue of which it opposes growth or decay of current flowing through it? The property of a coil by virtue of which it opposes increasing current, it opposes decreasing current, it opposes any change in current, but it does not oppose the constant current, right? So the property of a coil by virtue of which it opposes any change in current flowing through it, any change of current flowing through it. So that is actually called the self-induction. Simply, whenever the magnetic flux linked with the coil changes, an EMF induced in the same coil, that is called self-induction. Now, tell me, so how does the magnetic flux depends on the current? Actually, the magnetic flux, how does the magnetic flux depends on current? Magnetic flux linked with the coil that is directly proportional to current flowing through it, right? How does the magnetic flux depends on the current flowing through the coil? Magnetic flux linked with the coil is directly proportional to the current flowing through the coil. Okay, if the current flowing through the coil is gradually increases, the magnetic flux linked with the coil is also gradually increases. If the current flowing through the coil is gradually decreases, the magnetic flux linked with the coil is also gradually decreases. Okay, so the magnetic flux linked with the coil is directly proportional to current flowing through it. So this point is very, very important. The magnetic flux linked with the coil is directly proportional to current flowing through the coil. So remove the proportionality, so we will get the proportionality constant, that is L. L is the proportionality constant. So L is called the coefficient of self-induction. Coefficient of self-induction. That is also called the self-inductance. Self-inductance or the coefficient of self-induction. So, what is the meaning of the self-inductance? Self-inductance is magnetic flux per unit current flowing through it. Magnetic flux linked with the coil, 1 unit current flowing through it. Magnetic flux linked with the coil, 1 unit current flowing through it is called the self-inductance. Self-inductance is measured in terms of Henry. Henry is the unit of self-inductance. This is the unit. Symbolic representation is H, capital H. So 1 Henry, that is exactly equal to 1 Weber divided by 1 ampere. Okay, 1 Henry is equal to 1 Weber per ampere. So what is the SI unit of self-inductance? Henry or Weber per ampere. So, but according to Faraday's second law of electromagnetic induction, E is equal to d phi by dt. So this is the magnitude of induced EMF. So E is equal to d by dt of what is the value of phi? Phi is Li. So L is constant, that is stayed as outside. So L into di by dt. So L is equal to E divided by di by dt. If di by dt is equal to 1 ampere per second, then self-inductance, that is equal to E. Okay, self-inductance, that can also be defined as self-inductance is numerically equal to EMF induced in the coil when the rate of change of current, what is this? Rate of change of current flowing through the coil, that is unity. So this is another definition of self-inductance. Self-inductance is numerically equal to EMF induced in the coil. Self-inductance, that is numerically equal to EMF induced in the coil when the rate of change of current flowing through the coil is unity. Okay, so based on this equation, 1 Henry, that is exactly equal to 1 volt divided by 1 ampere per second. So volt per ampere per second. So this is another volt second per ampere. Is it not? Volt second per ampere. Okay. So or volt divided by ampere per second. So this is another unit of self-inductance. Okay, when the self-inductance of a coil is said to be 1 Henry, if 1 volt of EMF induced in a coil when the rate of change of current flowing through the coil is 1 ampere per second, so then the self-inductance of a coil is said to be 1 Henry. 1 volt of EMF induced in a coil, 1 volt of EMF induced in a coil when the rate of change of current flowing through the coil is 1 ampere per second. Suppose 1 millivolt of EMF induced in a coil when the rate of change of current flowing through the coil is 1 ampere per second. So what is the value of self-inductance? That is 1 millihenry. Henry is much larger unit of self-inductance. The smaller units of self-inductance is millihenry, microhenry. So what is the meaning of microhenry? When self-inductance of a coil is said to be 1 microhenry, if 1 microvolt of EMF induced in a coil when the rate of change of current flowing through the coil is 1 ampere per second, then the self-inductance of a coil is said to be 1 microhenry. Okay, what is the dimensional formula of self-inductance? Dimensional formula of self-inductance. So the dimensional formula of self-inductance. Phi is actually BA divided by I. But F is equal to del sine theta. Is it not? B is F divided by IL. B is F divided by IL A I. Okay. Now we can easily calculate the dimensional formula of self-inductance. Force means mass into acceleration. So mass dimensional formula M, acceleration dimensional formula L, T power minus 2. So what is this? Area dimensional formula is L square, right? So current dimensional formula ampere. So here I into I square. So dimensional formula of I square is A square. That means 2 in ampere. And dimensional formula of length, that is the L. Okay, so 1L get cancels. So finally, the dimensional formula of self-inductance is 1 in mass, 2 in length, 2 in length, right? 2 in length, minus 2 in time, minus 2 in time. And A square is shifted to the numerator. What happens? A power minus 2. Minus 2 in ampere. So this is the dimensional formula of self-inductance. 1 in mass, 2 in length, minus 2 in time, minus 2 in ampere. And this is very important for CET. Okay. So 1 in mass, 2 in length, minus 2 in time, minus 2 in ampere. So this is very important for CET. So what is the meaning of self-induction? Whenever the magnetic flux linked with a coil changes, an EMF induced in the same coil. The property of a coil by virtue of which it opposes growth or decay of current flowing through it. The property of a coil by virtue of which it opposes any change in current flowing through it. The property of a coil by virtue of which it opposes increasing current or decreasing current or any change in current. That is the meaning of self-induction. So what is the meaning of self-inductance? Self-inductance is the magnetic flux linked with the coil when unit current flowing through it. Self-inductance of a coil is numerically equal to EMF induced in the coil when the rate of change of current flowing through it is unity. So when self-inductance of a coil is said to be 1 Henry, if 1 volt of EMF induced in the coil when the rate of change of current flowing through the coil is 1 ampere per second. So the device which works on the principle of self-induction, so that is choke. Okay, choke is a device which works on the principle of self-induction. What is the principle behind the working of choke? That is self-induction. Okay, so the device which works on the self-induction is choke. Choke is a device which works on the principle of self-induction. So this point is also very important. Okay, thank you.